Many believe these X's are just decoration, but they are the secret to surviving an 8.0 magnitude earthquake.
Every single day, a massive invisible war is being fought. It happens right above our heads in the wind and deep below our feet in the earth. Skyscrapers are constantly under attack by the unstoppable forces of nature. Wind tries to push them over while earthquakes violently shake their foundations. When we look at a tall building, we just see a beautiful, peaceful grid of glass and steel. It looks perfectly still and immovable. But to a hurricane or an earthquake, a high-rise is just a giant, fragile lever sticking out of the ground, waiting to be snapped in half. If a building's internal skeleton is constructed merely as a simple grid of vertical columns and horizontal beams, it carries a fatal geometric flaw. A square is visually pleasing but structurally vulnerable. When a massive lateral force, like a seismic wave, hits the base of the building, those perfectly straight 90-degree joints act like loose hinges on a door. The intense pressure forces the 90-degree angles to bend and warp. The columns begin to bow under the shifting weight. In engineering, this dangerous bending is called column buckling, or simply pandio. The square collapses into a slanted diamond shape. The entire floor tilts, and the structural integrity is completely lost. We call this invisible assassin shear force. It is a massive sideways attack that tears a building's skeleton apart from the inside. If left unchecked during a major earthquake, this dynamic force will pancake the entire structure, turning millions of dollars into twisted metal. To defeat shear force, engineers realized they could not just keep adding thicker steel. They had to change the fundamental geometry of the design. They introduced the ultimate unbreakable shape of the structural world into the building's core, the triangle. A triangle physically cannot deform without its sides actually snapping in half. It is a master of weight distribution and an unyielding geometric shield. By taking a vulnerable square frame and running a single heavy steel beam diagonally across it, that empty wobbly space is permanently locked. But earthquakes violently shake back and forth, and high winds constantly changes direction. One single diagonal line isn't enough to secure a tower, so to ensure total 360-degree protection, we add a second diagonal beam, crossing right over the center of the first one. This creates the iconic massive steel X you see on the outside of so many modern high-rises. This is the mighty cross-brace. Let's look at the internal forces. Imagine an earthquake violently jerks the building to the left. Immediately, the building wants to tip right. The diagonal half of the X pointing away from the force is stretched tightly apart. It pulls back against the leaning corners, holding them together. It acts exactly like a giant steel rubber band fighting to keep the building straight. In civil engineering, we call this pulling force tension. At that exact same microsecond, the other half of the X is being crushed inward by the weight of the leaning structure. This beam acts like a massive shock absorber, taking millions of pounds of force. This dangerous compressive force is called compression. The magic is in the load transfer. The destructive shear force hits the horizontal beam, travels down the X, and is driven safely into the foundation. As a seismic wave rolls through and the building sways back and forth, these two intersecting beams instantly swap roles in a beautiful, invisible mechanical dance. The beam in tension instantly switches to compression, and vice versa, constantly keeping the building in a state of dynamic balance. You might wonder, why not just build thick, solid concrete shear walls instead of using exposed steel X-braces for stability? Because humanity desires light. People living and working inside want towering glass windows, massive open spaces, and breathtaking views of the horizon. The crossbrace achieves the impossible. It delivers the impenetrable structural strength of a solid concrete bunker while leaving massive voids for light to pour through. It is a masterpiece of structural efficiency, a perfect marriage of mathematics, civil engineering, and design, standing silently so we can live safely in the clouds.